Working on bounded error quantum branching programs, and this result shows that intuitively that I will remind that with two quantum branching program can be constructed using only one qubit, and it means that one qubit computations as powerful as NC1 circuit, which is interesting itself. And now I would like to speak on unbounded error simulation of quantum branching program. So let us define these classes as classes of Boolean function computed by bounded error and unbounded error stochastic branching programs, and this is class of Boolean functions computed by unbounded error and bounded error and unbounded error quantum branching program of polynomial size. So, and the results are the following. So we have these conclusions, and to prove this, we need the following. So it's okay. Now we have so it's stochastic and quantum branching programs. So stochastic branching programs use norm 1 for defining acceptance criteria for them. We call it type 1, and quantum branching program use norm 2 for defining acceptance criteria. We call it type 2, and the result is the following. So using unbounded or bounded error quantum branching program, we can simulate them stochastically with, and we use unbounded error criteria with these characteristics. So I sketch the proof. What do we need? So this is what we have in case of stochastic branching program, and this is what we have in case of quantum branching program. So step by step we relax, having quantum branching program, we relax these conditions. This condition, this condition, this condition, and these procedures. And the main procedure is that one. So, and how we can construct equivalent, in some sense, stochastic matrix instead of having unitary matrix, which gives us the property that the final branching program computes the same Boolean function. So, and these two first steps are standard enough. So it's this is again what I talked about, and the first step when we switch from complex presentation to real, say, presentation, we just double the width of space. And when we switch from using norm 2 to using norm 1, then we use this known property, which gives us the square of the width, and the main is construction of how to go to switch from unit now real valid. Now first two stages gave us the following some real valid matrix, and now we go with matrix M, and we would like to construct corresponding stochastic matrix W as follows. We add one column and two columns and two rows with a prop, and we fit these rows and columns in the following way, that the matrix A which we got should be 0. It means that the sum of elements in each row should be 0, and sum of elements in each column should be 0. This can be done easily. And next stage we add double stochastic matrix, which is usually called unimodular, unimodularny, and in the following way. So we multiply elements of matrix A by small constant C to make it smaller than each elements of matrix R, and then we have that corresponding matrix became stochastic matrix, and that's it. So it's, and now we can play with the threshold of computation, and we can play with the start nodes and accepting set of indexes in order to fix the model which should compute the same Boolean function. So finally this gives us the proof, and where we lose the bounded error criteria, we lose it here when we get at last this coefficient, small number c between 0 and 1, power L, where L is the length of branching problem. So this kills the so-called isolation cut property. Okay, so maybe I will skip this, and in order to finish, and so I'd like to finish with this funny picture also, that which was, this information was not discussed in our seminar here, but so it's, I think all of us heard on this, that Canadian Harry can say more, I guess, on this.
What?
Did you hear on this?
Sure.
Yes. But what do you think on this?
It's a host.
Yeah. Sasha, in February, Canadian corporation, which is known as D-Wave Systems, announced that it already produced a real quantum computer, and it's 16 qubits. 16 qubits, and it's going to sell it. So the market is open. And this picture gave me Mika Hirvinsau, which is, he's written quantum computers. So I asked him where he found this picture, and he told that somewhere in Serbia. So if you are going to buy quantum computers, so go to Serbia.
Yeah, but it's definitely that they say commercial.
Yeah.
So the only criterion which we are allowed to apply to them is their commercial success, which probably is not that bad.
Yeah, so but all time
they collected a lot of money probably.
Yeah, commercial all times goes in the first stages. So it means that in 10 years we should have.
Well, I think it's bad actually, this company, because they claim to be able to do 16 qubits. And they actually have a demonstration where they solve a Sudoku problem.
For next year, they promise to have computers for 100 qubits.
But nobody really knows what's in the box, and it's very unlikely that they actually have a...
Probably they make first some classical reduction, and then they apply for quantum computing.
So I think it's actually very bad for the field.
And then there is a dwarf sitting in the box and solving all the problems. Good times with chess machines.
It can be compared to people selling land on the moon, you know, there are such commercial successful.
Okay, any questions? Thank you.